webcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and thank you for attending today's webinar. It's VisiMix's pleasure to have Dr. Victor Atiemo-Obeng conduct a series of webinars addressing how early considerations of mixing in stirred vessels can help process development chemists and engineers achieve significant process improvements. During this lecture, you'll be able to write your question in the chat box and we'll address them at the end of the webinar. In the event, though, if you have any questions for VisiMix staff about VisiMix, we will note them and our technical expert will get back to you via email. Today's webinar will focus on mixing science and practice in the chemical and allied industry. We hope you enjoy today's webinar. Please, Victor, whenever you're ready, you can start.
Okay, well, good day to all of you. I understand people are from all corners of the world, so it's for some it's good morning, others is good afternoon, for some it's good evening, and sometime for some others it may be even getting ready to go to bed. Anyway, so good day. Anyway, I hope you can all hear me well. Marcy, can you hear me well? Will somebody give me a sign, please?
Yes, I can hear you, Victor.
Very good, very good.
Right.
Thank you, thank you. All right. Okay, all right. Well, so as I said, good day to everybody. I offer to assist VisiMix in presenting a series of webinars, and as Marcy said, we're going to be talking about mixing science and practice in the chemical and allied industry. Now, I mean, I believe most of you are interested in VisiMix, the set of tools that VisiMix provides. But in my discussions with VisiMix, I suggested that we start out with just looking very broadly at the mixing science and practice in the chemical and allied industry first. And this way, when the next time when we talk about VisiMix as a productivity tool, you will appreciate the scope of it, what it's able to do, and so on and so forth. But also, I also believe that to use a tool, you really have to understand the context in which you are going to apply the tool. So that's what we're going to spend some time on today looking at. So mixing science and practice in the chemical and allied industries is the topic. Now, a typical processing example is shown here. And what you see basically is a series of reactors and centrifuge and a dryer and so on. And I borrowed this from another presentation. And you see that there is blending in the first reactor, there is blending of reagents A and B. You heat and react to form C, and then you transfer it to the second reactor, and you blend in another reagent D, and you react with C to form E, and then you follow on and so forth. So the thing is that for the process to be successful, you see that for the blending and the reaction and the heat transfer and all of that, the cooling and crystallization, there is a device in there which we normally call a mixer. Okay? So it's important for the success of the process that the mixing is done effectively. That's the key message, one of the key messages that I want to share with you today. Now, if you look at the chemical and allied industries, there's really a variety of equipment that is classified as mixing equipment. And this is just a list of some of these things. Obviously, we're not going to cover all of these. We're going to focus on stirred vessels, and you'll see that very soon. But the key point here is that to use these equipment effectively, you really need to understand or have the knowledge of performance characteristics, the effective process application ranges, and their design features. We're not going to cover any of these in this particular presentation, but the next webinar, when we talk about Visimix, I think you begin to appreciate what I mean by the performance characteristics, application ranges, and the design features. The key piece of equipment that we're going to be focusing on is the stirred vessel. And it's typically used for batch processing, but it can be used in series as a continuous process also. These are some comments that have been made by various people about batch processing. Ripon says that significant proportion of world's chemical production by volume and a much larger proportion by value is still made in batch plants. And so we depend on this device, this stirred reactor, basically a vessel with a stirrer in it. It's key really in the industry. And then recently, 1997, Bigler and Grossman made the comment that with the recent trend of building small flexible plants that are close to markets of consumption, there's been renewed interest in batch processes. Now, this is not to say that continuous processes are also not on the upswing, but the main point here is that this is the key piece of equipment that we're going to be looking at. And of course, in that piece of equipment, there is a variety of impeller types and so on. Today, we're not actually going to spend any time at all describing these various impellers, apart from this one slide here. When we get to the device itself, the next webinar, we can talk about some of these impellers and how they're used. But this slide shows you some of the typical impellers that are used and what they are usually effective for. Okay? So, if you are a process engineer, and I don't know all who are signed up for this webinar today, so I don't know your background. But if you're a process engineer, quite often your focus is on the pieces of equipment itself. When I first started studying mixing, and which I did at Dow when I worked there, it became very clear to me that it's misplaced to focus initially on the equipment. I think it's more important to look at the process, and particularly to ask some of these process-related questions. So these questions seek understanding of the important phenomena in order to apply the necessary engineering science. And if we do that, then we are able to achieve the desired process results. The questions lead to identification of the potential risks in scale-up as well as process operation, and thus the preparation of appropriate contingency plans for risk management. So in this webinar, we're going to be looking at some of these important mixing phenomena. I don't suppose it's a surprise to see this slide here, listing processes requiring stirring or mixing. I mean, there's a variety of processes that are carried out in the chemical and allied industries, and some of these are listed here. This is by no means an exhaustive list. But the thing that that I have always felt the need for is that a way to categorize some of these processes in a way that it makes it easy to handle or to manage. And the primary categories that I always look at are that you have miscible phases that are dealing with blending with or without reactions. And then you have multiple phases also with or without reactions. And it's important to look at if these two categories because I think the requirements are very different, and it it helps when you are looking at your process to start with this kind of categorization. Um, the complexity will become very clear very quickly when you if you do not pay attention to these different categories and so on. So anyway, let's start out by asking the question, what is the purpose of mixing? We carry out mixing in processes to affect a process in a desired manner. For example, we blend miscible fluids to make concentration and temperature more homogeneous in the vessel. But at the same time, whilst we're doing that, we may do this to enhance the chemical reactions and also control the reaction selectivity. And we'll talk about some examples later on. We can also carry out mixing to suspend solids in a liquid, and that may be all we do to create a uniform suspension that we then transfer into another tank for something else. But we may also carry out suspension of solids in a liquid. For example, if you have catalyst, you want the catalyst uniformly distributed in the reactor. Or if you're feeding a centrifuge, you want to suspend the solids so that you can feed a uniform concentration of solids to a centrifuge. We may also want to create a dispersion of a liquid, one liquid in another, oil and water, or disperse the gas in a liquid. And in some cases, there will be multiple of these events or desires for the process to be successful. And we need to pay attention to that. There was a time at Dow when I actually tried to ban the use of the word mix because it's so vague, it's so loaded, and it does not give you any indication as to what the desired outcome of the operation, of the mixing operation. So instead of saying mix, I would like to suggest that when you're talking about your process, that we use words like some of these words that I have listed here on this slide, blending to achieve a certain objective, enhancing chemical reactions and so on. Okay? So let's define mixing. It's a process operation where mechanical energy induces fluid motion in a volume of fluid in order to reduce inhomogeneities of the fluid's properties to achieve a desired process result. This has been a working definition that I've used all the time, the 34 years that I was at Dow. And it served a purpose because what I've tried to do is encourage people to avoid the use of the word mix in describing what occurs in the process vessel. And instead, use words that will help them describe what is happening in the process, in the fluid. My mentor used to tell me that it's good to imagine that you are a Maxwell demon attached to a molecule in the fluid and experiencing various phenomena. And if you are able to describe the phenomena that is occurring whilst you're floating around in the vessel, I think it gives you a much better insight as to what is happening and what you need to do to be successful in your process. So with that definition then, we see that a mixer converts mechanical energy into kinetic energy to induce a hydrodynamic environment in the vessel. There is bulk or macro flow occurring in the vessel. There are microflow turbulent eddies that are also occurring. And as a result of the different velocity gradients and so on, there's shear stresses and strains that are also occurring in the vessel. And what we need to do then is to make use of all of this. The challenge is to understand these hydrodynamic environment and select and design a mixer to create the environment that is best suited for the success of the process. So the goal then is to use the energy efficiently, to convert the mechanical energy efficiently to create the appropriate hydrodynamic environment. This is a slide that I borrowed from a manufacturer of mixers, Cato. They have a handbook of mixing technology, and if you look at these three panels, you see shown in here descriptions of descriptions of three different impellers, and also showing the very broad distribution of power locally in the vessel. In the panel on the left, the highest energies are concentrated around the tip of the impeller, and this is usually the case in most vessels. In the middle panel, you see a much broader distribution of energy, local energy distribution. And in the third panel, the panel on the right, you see it's even more uniformly distributed. So the question then is, these are all different impellers, and you see the distribution of energies that are shown in here. And so, as I said, the challenge here is to pick the impellers and operate them in a manner to give you the environment, the hydrodynamic environment that is most best suited for the process that you need to carry out. This quotation on this slide comes from a paper. Actually, it's a commentary written by the late Professor Octave Levenspiel. Levenspiel is famous for writing or publishing some reaction engineering textbooks. Very well known, very famous. Anyway, just a couple of years ago, Professor Suzanne Krestov in Canada, this paper was one of the most read articles from the Journal of Industrial Engineering, Chemistry and Research in 2011. It's actually instructive that Octave Levenspiel did not use the word mixing, and instead used flow patterns and contacting, that is hydrodynamics. Further, he did not say chemistry, instead he said kinetics. His message is one cannot design an effective reactor without paying close attention to the hydrodynamics, flow patterns, and contacting. So the lack of knowledge of the complete kinetics may not be as consequential. My experience is indeed very true. One can have the complete kinetics, but if the necessary hydrodynamics are not realized, the results can be disastrous. So effective mixing generating the expected hydrodynamics is required for success. Now, the hydrodynamics in a vessel can be classified as laminar or turbulent. And indeed, when we talk about Visimix in the next webinar, you will find out there are two sets of tools, one that is devoted for laminar mixing and one that is devoted for, actually a couple of them that are devoted to turbulent mixing. And the mixing, the hydrodynamic parameter that is used to describe whether you are in the laminar or turbulent is obviously the Reynolds number, which depends on the fluid properties, the density, rho, viscosity, mu, and also a characteristic fluid velocity in the vessel, and a characteristic length scale of equipment. Typically, in the mixing literature, you find that the characteristic velocity is the tip speed, or the impeller diameter times the impeller speed, impeller rotational speed. And the characteristic dimension is d, the impeller diameter. Now, Visimix does not use those characteristics, velocity and diameter, and we'll talk about that when we talk about the tools themselves the next session. But the point here is that the consequences of being in the laminar or turbulent flow needs to be paid attention, because the mixing mechanisms are different and the equipment requirements also differ. And you'll see that when we address the next webinar, when we talk about the Visimix tool. Now, most of you spend some time in the kitchen preparing various things. I want us to consider these cases in describing mixing processes. Preparing a drink, rum and coke, or sweetening tea and coffee with honey or some granular sugar, or making salad dressing using oil and vinegar, or preparing bread dough, flour, and water. Now, when we do these things, and we use a variety of equipment, in the first one, we can just use a straw to stir your rum and coke, or a spoon to stir your coffee, and when you add the honey or the granular sugar, to dissolve the granular sugar or the honey and distribute it, blend it in uniformly so that the first sip is as good as the last sip. Or when you prepare salad dressing with oil and vinegar, whatever tool you use to distribute the oil into the vinegar. The key point here is that in each case, when we do these things, we use the word mix or stir. But it's very obvious that we are dealing with totally different phenomena. In the rum and coke, sweetening tea and coffee, making salad, and so on. So it's important that we focus, when we're describing mixing, to focus on first the desired process outcomes. In the rum and coke, we are blending two miscible liquids. When we're sweetening tea or coffee with granular sugar, we are actually changing the phase of the solid. Granular sugar is dissolving and then blending into the tea to make to uniformly distribute the sweetness throughout. In making salad, obviously we are creating droplets of one fluid in another. In making bread dough, we are actually wetting the particles and swelling them somehow and then mixing it to prepare the dough. So the phenomena occurring are all very different. So when we just use the word we are mixing, we lose some very important message or important concept or important aspect of the phenomena that are occurring. Also, we lose out the time scales and the length scales that are involved, or the difficulty and the challenge in carrying out these four different activities. And of course, the equipment used are all very different. And you find this to be the case in industry. So this is something that we need to pay attention to. When I was down, one of the things that I kept pressing, telling people about, is that when you're doing process R&D or scale up, you need to pay attention to both physical properties, phases, densities, viscosities, and rheology. And of course, the chemistry whether you have chemical equilibrium or you have some kinetics, fast or slow kinetics, you pay attention to all of those. But then also, as we've mentioned, as I've already mentioned in previous slides, the hydrodynamics and the various other phenomena, transport phenomena that are important for your process, mass transfer or heat transfer. If you do not pay attention to all of these things, the likelihood that something is going to bite you and you're going to suffer in achieving the success in the process that you desire. So here again is a list of various processes that are carried out. And as I said, this is not intended to be exhaustive in any way. I'm sure you can come up with other things that we can add to this list. But one of the things that I learned in my time at Dow is that it's important to have in mind some key steps in addressing mixing in process development or in the process plant or anything like that. Always start with addressing or identifying the desired process result and find a way to link that somehow to the purpose of mixing. Now, once you do this, then the next stage is to perform some analysis. The analysis could be either experimental or you could do some modeling. People do computational fluid dynamics sometimes. But there are also tools, other tools that you can use, some simpler tools like Visimix, which we'll talk about the next webinar. So once you do this analysis, then you're doing this analysis to confirm or to identify the mixing phenomena that are occurring and how it relates to the process, the desired process result. Once you do that, then you can then recommend or select equipment and operating conditions that would be best to achieve the desired process result. And after you've done that, you need to ascertain the reliability of the mechanical design. You will find out that Visimix tool allows you to do all of these things that I have listed here. Sometimes the folks at Visimix will tell you that using Visimix, you can avoid doing experiments. And I tell them that's not true. You can minimize the number of experiments that you do, but it's always good to confirm some of these things that you determine with experimentation. I mean, obviously, there are some processes which you get a very good understanding with your modeling or your calculation with the tools and so on that it may be okay to avoid the experiment. But I think in general, my recommendation always is that once you think you have determined the best equipment, the operating conditions and so on, to test something, to test it experimentally to confirm, have confidence, because the consequences are very important. Having a good process, a working process, achieving the desired yields, selectivities, and so on, is what we desire. And so that's very important to test it if you need to. So now let's take a look at some of these different phenomena of mixing phenomena that occur in various mixing equipment and stir vessels. The first one we're going to look at is the phenomena of blending. In this slide, you see snapshots of blending in a stirred vessel, and note the time and length scales associated with the non-uniformity of concentration. Now, normally we make the assumption quite often that blending happens instantaneously. Well, you can see even after 1 second, the vessel is not uniformly colored with a dye. note the location of where the dye comes in. If I could get my cursor, right here is where the dye comes in this particular, if you can see my cursor. And as I said, after 1 second, the dye has not spread uniformly throughout the vessel. There are pockets of very high concentrations and vice versa. There are pockets where the dye hasn't even reached yet. So if the dye were to react, reaction rates will vary throughout the vessel because of the difference in concentration. If there are multiple competing reactions that are faster than the mixing action, the outcome may be different from what is desired. And there's one slide that we'll take a look at that. Eventually, the dye will be uniformly distributed and at an average concentration everywhere. The rate of dye distribution and the concentration profiles will be different if you add the dye in a different location, say near the top and far away from the impeller blade. If you use a different impeller, if you add at different rates, if the additive, the reagent that you're adding has different fluid properties than what you're adding it to the bulk, the speed of the stirrer, its size, design, location, and so on, the vessel internals, such as whether you have baffles or heating and cooling coils. So again, one needs to pay attention to all of these. If you look at solid liquid mixing, the goal is to suspend particles. In other words, pick up the particles from the base of the vessel. Because if they are denser than the liquid, they want to settle. And your goal is to pick them up from the base of the vessel and separate them. If you have very light solids, the challenge will be to wet the solids. In other words, spread the liquid all over the entire surface, or to draw down the particles from the liquid surface into the fluid. This is something that early in my career I came across courtesy of Lightning, another company that made mixers. And I showed these 3 panels here. They show the 3 panels of three tanks, same dimensions, with 3 different impellers in there, impeller sizes, with different U over T's, impeller diameter to tank diameter, and operating at different speeds. And the performance of the impeller in its ability to suspend these solids vary significantly. In each tank, you're putting in the same amount of power, but of course, the torque as it's defined there is very different. In fact, the biggest torque, in other words, the vessel that will require the biggest gearbox, is the panel on the right. And yet, that's the one that if your intent is to lift particles up, that's the one that does the poorest job. I don't know whether these videos will play, so I will avoid them for now. Let's move on. Okay, let's go on. But anyway, another feature here is that when you suspend solids, you want to determine the degree or level of suspension. On the left is partial suspension, complete off-bottom suspension in the middle, and then if uniform suspension. Now, we never really truly achieve complete uniformity of suspension, but we approach it. And depending on your process, any of these may be suitable, may be acceptable. For example, partial suspension may be acceptable for dissolution of very soluble solids. You don't need to lift them all up. If they're very soluble and you keep swelling them at the bottom of the vessel, that would be sufficient. And so that's what you do. Another phenomena, liquid-liquid dispersion, where you're taking drops and breaking them up. But when the drops meet each other, they coalesce, depending on the force of collision and so on, and the viscosity of the fluid between them. They can coalesce and form a bigger drop. So this process is going on, both drop breakup and coalescence is going on. But you also want to distribute these drops in the vessel uniformly, depending on the process that you're carrying out. So drop breakup and dispersion requires a threshold of energy. You need to put in a certain minimum amount of energy before you can actually break drops. It's easier with bigger drops. It's facilitated in liquids with lower viscosities and lower interfacial tension. So you can add surfactants and stabilizers and so on. But the drop coalescence and aggregation will continue even when you're breaking drops out. And these are also influenced by the energy input and the properties of your fluid. This is a challenging area for processes, but you find when we talk about Visimix in the next discussion, we find out that we're able to use Visimix to actually do some drop size calculations and distribution and so on. And so we'll address some of the physics that are involved in it when we get there the next webinar. Liquid-liquid dispersion, the process objectives will vary according to the desired product, but they would include all of these things that are listed here. The nature of dispersion, whether it's oil and water or water and oil, or sometimes complexes like oil and water and oil, and so on. The drop size distribution that you get, the time it takes to reach a certain equilibrium drop size, the stability of the dispersion, and the tendency to resist the coalescence rate that is occurring. Some of these things are very challenging, and I don't know of any tools that are out there that are able to address all aspects of liquid-liquid dispersion yet. In gas-liquid mixing, we are also doing breaking up bubbles. We bring gas in and we want to break up the bubbles into small bubbles to create interfacial area and distribute them uniformly throughout the vessel, again, to affect the process that we are carrying out. And then for reactions, mixing affects how reactants are brought together, and they determine the local concentration and temperature, reaction rate, and other properties. And thus it affects the course of the reaction rate and selectivity. For single reactions, blending can affect concentration of reactants and that reaction rate. For multiple reactions, blending can also affect the selectivity. For multiple systems, mixing affects drop and bubble sizes and thus the interfacial area for mass transfer. So it's important then to vary mixing in your studies to determine the effects of mixing and to determine which is important. Here's an example. This is something that you've seen many times before, some of you. But we have a case, these two reactions, the desired reaction is A reacts with B to form R reacts with B to form S. And let's suppose that you've segregated reagents A and B perfectly. Let's say with some special membrane. Then you take out the membrane. Now, you can see in this left panel here at the bottom, sorry, what happened? Oops. There. These two A's will react and form R. But if there's no further if the mixing is poor, what you're going to end up then is that the R will react with B and you form S. And so what you will get is this condition which is most undesirable. However, if you have very good mixes, when you take out this special membrane and you have fully mixing of all the molecules, you can form only you'll be able to successfully form only R, and that's what you desire. This is an example from literature, Chemical Engineering Science, 1995, published by Baldiga. And the only thing he's doing here is two similar vessels, same impellers, and the only thing he's done differently is the location of adding of the reagents. It's a precipitation reaction is carrying out. In this one, the reagents are added right near the impeller. Here, the reagents are added on the top of the liquid. And you can see with the supersaturation profiles that the results of the products that you get are very different. With the sharp S profile here, many small crystals and non-uniform crystal size distribution are formed. With the broad supersaturation profile, you get larger and more uniform crystals. So again, it depends on what it is that you desire to do. Here's a case of a polymerization reaction, and all you're doing is changing the impeller speed, carrying out in this small vessel over here. The first time the chemist did it, he ran it at 150 RPM in this 98 degrees C. And he kept taking samples, and it seemed like nothing was happening, and he left it over many days, and then he saw that the reaction was taking place, but it was very slow. So when he sped up the speed, look at the changes that happened. The reaction is done, in this particular case, 700 RPM in less than 200 minutes. And here's an example. It's a very complex example where you're reacting in amine with chloroacetyl chloride, and you have sodium bicarbonate as a solid. This is a solid here in water. You try to provide a buffer solution and also to react the HCl that is formed in here. So it's a very complex reaction. You have solids, you have liquids, immiscible liquids, you have actually the product also is a solid, and you have gases that are released. By putting different number of impellers running at different RPM, varying the feed rate of the reagent and so on, you can affect the yield that you get. So the message that I want to leave with you is that mixing challenges require close attention. If you just, all you're doing is blending rum and coke, well, it's an easy objective and easily achieved. If you're doing scale up, it's important that you pay attention to what it is you're doing. If you have multi-phase systems, most likely you are going to have to address many scales of mixing, frequently mass transfer aspects, and always incomplete understood physics. So it's important to be able to use or to do experiments or to use a tool that gives you insights as to what is happening in your process. Also, when you have competing rate processes, these are also very difficult to scale up and design. Some of the mixing operations that I found most challenging are listed here. When you're blending higher density, higher viscosity miscible liquids into thin bulk liquids. Blending or reacting as viscosity increases and rheology changes. Incorporating or dispersing or dissolution of powders into viscous bulk. So these are all very challenging things. These are all miscible systems, but you can have these challenges. In solid liquid, incorporating or dispersing poor wetting solids into liquid. When the solids have a tendency to agglomerate, for example, polymer pellets during dissolution, when the outer skin contacts the solvent, it swells up and it gets tacky, and it would glom up other pellets and form an agglomerated mess. Achieving suspension of fragile needle-shaped crystals with minimal attrition, settling and packing of solids in vessel bottom, sometimes incrustation of solids on weathered surfaces during crystallization or precipitation. Predicting drop sizes for concentrated and surfactant-laden dispersions. Those are tough. And sometimes you may have catastrophic inversion of phases during formulation, for example. And then, of course, fouling or gel formation during emulsion polymerization. These are some of the things that I encountered in my time. So to conclude, some important lessons. Because mixing is very complex, as you've seen in these examples that I've shown you, process failure can happen. And it can happen if you don't pay adequate attention. And process failure is really the costly thing to encounter. From lower reaction yields, longer reaction times, unacceptable product properties, or making impurities that require higher cost for purifications and so on, or handling the waste. Higher production costs for product rework and so on. So, early and careful assessment is important. If you are able to do early assessment, you can affect your process in some very positive ways, because you can determine how to make changes quickly and avoid costly mistakes. And usually, if you're able to identify these mistakes early, the cost to make changes is much lower. The opportunity to influence the process decisions is very good. Avoid preventing process scale-up problems is important. And you'll be able to achieve your process goals and make money. And that's what we are after. So this requires then that you have some tools. Here are some resources. Some of the things that I've talked about are covered in much detail in these two books that I had the privilege of co-editing. But the resource that we're going to be looking at in the next webinar is Visimix. This resource allows you to very quickly assess mixing issues in your process vessel. And so that will be the topic of the next version. Now, this slide here shows you all of the interaction of mixing phenomena that you can perform with the tool Visimix. It will calculate hydrodynamics, determine the turbulence, energy dissipation inside the vessel, the fluid. We can do heat and mass transfer calculations. There's, in the suite of tools, you can do mechanical reliability calculations, stress and vibration. You can use the tool, once you determine the hydrodynamic, you can do liquid-liquid solid mixing, liquid-solid mixing, multi-phase systems, gas-liquid, and liquid-liquid dispersions, applying the hydrodynamic information and the turbulent information. And you can also address chemical reactions using information from the turbulence calculations and so on. And this is what makes Visimix such a productivity tool. And that's what we will look at next in this webinar series. So make sure you sign up to attend the next session, where the Visimix folks and I will talk about Visimix and productivity tool for successful research scale-up optimization of process and stirred vessels, September 25th. Thank you. And if there are any questions, I think we have some time to address some questions.
Are there any questions for Victor today? If so, then if you can please type them in the questions area.
So I
And
should look
we
at
have
the,
a few
I
more
should look
minutes.
at the chat. I
Yes,
should look at the chat.
there's a place to type in your questions. Each of you can see that. And we have a couple of minutes, so if there are any questions for Victor, we'd be delighted to address them.
I don't hear any questions. I don't see any.
They'll be typed in, so
Okay.
you won't hear them. But so I see somebody's raised their hand. Let's see. Let's just see.
Moshe is talking, but I don't hear.
No, it's me, Victor.
Oh, okay. All right.
Okay. So there's a question from Mr. William Penny. Can you type your question into the question area? Okay, so we have I don't see who's asked this question, but one person says, I don't have any questions, thank you. I will have some more
Okay.
questions
All right.
for the next webinar. So what I think we'll do is I think we'll wrap things up, and
Well, we still have about 6 minutes. So if there's people who have questions, maybe you can
okay,
answer them.
sure. If anyone can think of a question for Victor, we have a few more minutes. Okay. Durando said thank you. And Alessandro had said that he'll probably have some more questions in the second webinar.
Okay.
And Granco is asking, does Visimix cover solid dispersion as well as high shear mixing? Victor, do you want to address that?
Okay. Visimix will not cover just mixing of solids. But if you have dilute solution of solids in a liquid, Visimix covers that.
And for the high shear mixing, we also have a tool.
High shear mixing using devices like rotostators and so on is covered. Again, using rotostator mixers in stirred vessels is covered in Visimix.
And somebody had asked, can we get a copy of the slides?
Sure.
Okay.
That's yeah, absolutely.
Okay, so what we'll do?
So make a request to you.
Yes.
Or to whom?
Yes.
Okay. All right. Make a request. You can get them. Yeah.
Yes. So if you can send the presentation, Victor, and I'll send those out.
I'll do that.
Great. Okay, and let's see what else. Leandro said thank you.
Okay.
And let's see. I think that's about it for now, anyways.
Okay, good.
Okay, so we have another question. Hi, Victor. With regards to dissolving polymers in solvents for chemical recycling. Okay, I can't see the whole. Would you recommend Visimix or any other? I can't see the entire question. Modeling approaches.
Okay. All right. Okay. Any tool that is out there has limitations, obviously. All right. Now, Visimix will handle the solids distribution in the liquid for the polymer. Now, if your polymer, as I mentioned, if your polymer swells up and is very tacky and so on, now Visimix may give you some information about the shear stresses on the surface of the particles, but that it doesn't tell you whether that is sufficient to keep the particles from sticking to each other or not. For that, my experience is that you probably have to do some experimentation to find out. At Dow, I encountered cases where as soon as you add a solvent to a solid, they'll swell, clump, and stick to the bottom of the vessel. so there were other ways of handling it, and we could, I mean, if you could send me an email, we can talk specifically about that.
Okay, so we have another question from Hiram. Hi, Hiram. Will you be covering scale-up parameters in the next session?
With Visimix, yeah, we can look at scale-up. With Visimix, you can do any degree of scale-up that you want.
Right.
Really. So we can cover all of that in the next session.
Perfect. Great. Okay. Let's see. Let me just make sure I got all of your questions. I think that's it for now then.
Okay. Well, again, it's really a pleasure for me to work with Visimix and to share with you these concepts about mixing in the chemical and allied industries. Now, as I said, this was just to give you some background information about what occurs in those industries with respect to processes that require mixing. Now, next webinar is when we'll be addressing how we use Visimix to actually look at these processes and how Visimix can then serve as the productivity tool for you to supplement your experimentation to enhance your productivity also. Okay.
Thank you so much, Victor, and thank you everyone for attending. As Victor mentioned, the next seminars being given by Victor will be on September 25th and November 6th. We will be sending out invites for you to join the webinar closer to those dates. So thanks once again, and we'll see you soon.
Okay.
Okay. Good day, good night, good morning, everyone. Bye-bye for now.
Okay. Bye-bye.
Bye.